Hello everyone, my name is Litika. I'm working as a research scholar in the Upper Institute of Engineering and Technology, India. I would like to thank everyone for giving me this opportunity to present our topic numerically stable iterative methods for computing matrix sign function. This is the overview of today's presentation. Let's start with introduction. Basically, for the study of matrix sign function, we came up with the matrix function. So basically, functional matrices have been studied for long as matrix algebra itself. Indeed, in his seminal, Cayley investigated the square root of matrix. It was not long before the definitions of function of A for journal left that were proposed by Celestine Frobenius and others. From their origin in pure mathematics, matrix functions have broadened into a subject of study in applied mathematics with widespread applications in science and in engineering. Research on matrix functions involved matrix theory, numerical analysis, approximation theory, and development of algorithms. So it employs a wide range of theory and methods that promotes an appreciation of all these important topics. Basically, matrix functions play an important role in many applications, and some of them are listed here. That in the field of differential equation, exponential interrogators, nuclear magnetic resonance, Markov models, control theory, pseudospectra, and etc. The matrix function of any assigned matrix is formally defined by Cauchy-Dagger formula as given in expression 1, where f is an analytic function in a closed loop sigma that envelopes each eigenvalue of A. This formula is difficult to understand when it comes up to discovering the matrix function and necessitates to study complex analysis. So as a result, various different techniques for determining matrix function have been developed and researched, like the Jordan canonical form, polar decomposition, and others, which can be seen in literature. For the study of matrix sign function, we should know the definition in the scalar case. So basically, in the sign function for any zeta, not lying on imaginary axis is defined by this as given in equation 2, and moreover for any matrix A that should be square matrix that can be decomposed into product of two matrices, that is S into N, whereas denotes the matrix sign function, and half is the principal matrix square root of the matrix. Matrix sign function has a lots of characteristics, and few of them are provided here. That matrix sign function is involutory and diagonalizable, corresponding to eigenvalues plus minus 1. Moreover, it has a commutative property. And if A has real entries, then so is L, so is S. So these two are the projections onto invariant subspaces that correspond to eigenvalues in the left and right half plane. In literature, Newton method is used to find matrix sign of any non-singular matrix whose expression is given as in equation 4. The basically Newton's method has quadratic rate of convergence. This method is very useful. But next, the Canny and Loeb provided a significant journal family of matrix iteration to find matrix sign function using the paid approximation by using the polynomial 5 and 6. Then he came up with the journal iterative expression as given in equation 7. This method has basically r plus s plus 1 convergence order, and this converges towards plus minus 1. From the expression 17, we can retrieve well-known method, that is Newton-Schulz and Halley's method given in equations 8 and 9, because these are part of paired or their reciprocal. Also, the Newton method is also a member of reciprocal paired family of iterative expression. Generally, the iterations of Kane and Loeb are globally convergent, and few of them are listed here. But this is not necessary that the each member of Kane and Loeb is globally convergent. So basically, some of them are not like Newton-Schulz method, that is not globally convergent, that we will prove later. And this for to improve the performance of existing methods, we consider some four-step structure of Newton's type method to solve the following matrix equation given in equation 10. For the construction of new matrix iterative scheme, basically we have two roadblocks in our way. The first one is the uniqueness of the obtained matrix iteration. That means it must not be identical to any of the constituents of the journal family of pair or their reciprocals. And the second one is the global convergence behavior. So we considered the expression 11, that this is a new matrix iterative function, and this requires a 7 matrix multiplication. So in order to reduce its cost, we perform another form of it as given in equation 12. That is, since this expression 12 has only 6 matrix multiplication, now we achieve our second aim, that is the global convergence behavior. For that, we draw attraction scenes for the proposed method and corresponding to the scalar nonlinear equation Gx. We color each point in a rectangle D based on the simple 0 plus minus 1, at which the iterative technique starts at Z naught converges, or mark the point as black if the method diverges. The stopping criteria used in this section for the method to converge is this, with the maximum iterations 25. So these are the figures corresponding to the four methods: Newton's method, Newton-Schulz method, Halley's method, and the newly proposed method. So can we say that Newton-Schulz method is good? No. Why? Because in this figure, Newton-Schulz method, this has a lots of black spots or divergence region, due to which it is not globally convergent, while other methods are globally convergent. So we have obtained the two achievements, like the method is new and it is globally convergent. So let's discuss its convergence analysis. For that we prove this theorem, that consider a set containing imaginary eigenvalues of initial matrix X naught as empty. Then the sequence of matrix iteration from 12 converges to sine function X. So for that we suppose some t as a rational function with which the 12 is associated, and we know that for any complex matrix X, the Jordan canonical form can be written such that there exists some invertible matrix V. We obtain some X equals to this, and then accordingly we get expression 30. So basically using 12, the eigenvalue beta of xk is mapped into the eigenvalue t beta of xk plus 1. Because of the eigenvalue scalar relationship, we must investigate how the complex plane is mapped into itself by t beta. The rational function t, to be precise, must satisfy the following two properties, that is the preservation of sign and the convergence should be global. So to prove this, consider A has a Jordan canonical form as given in equation 14, such that V is non-singular matrix. C and N are Jordan blocks equivalent to eigenvalues in this. The values located on principal diagonal of block C and N are denoted by beta is. And using 14, we have expression 15 and 16. Now consider that D naught is equals to V inverse AV, and accordingly we can generate a sequence decays such that converges to sine of lambda, and from expression 12 we can obtain expression 17. Now consider that D naught has entries on its main diagonal, and all the subsequent decays are also diagonal as well. So to solve f of x, we express 17 in form of an uncoupled scalar iterative technique as follows by equation 18, where this we can analyze the convergence behavior of decays to sine of betais. So with the assumption of eigenvalues, we can obtain expression 19, which show that it is bounded and under some conditions that the mode value of this is less than 1. This shows that the dki's are converging towards sine of betais, and accordingly we can say that the as limit k tends to infinity, dk is converging towards sine of lambda. So similarly, d naught, if d naught is not diagonal, we can prove accordingly that the method gets converges towards sine of 8 as given in expression 23. Now, assuming the same hypothesis as considered in theorem 1, we prove that the proposed method has a sixth order of convergence. So we know that the xk is a rational operator of A, and hence it satisfies the properties of matrix sign function. And using the properties given in equation 24, and after using some algebraic calculation, we can obtain an expression 27, which shows that the new method has sixth order of convergence. Now we prove that the method is numerically stable. That means over a small perturbation, the method is numerically stable or not. So for that, the sequence xk formed by expression 12 is asymptotically stable under the identical consumptions as given in theorem 2. So if the initial condition x naught is equals to a, then from 12 the obtained iterate is also a function of a. Hence, it satisfies the commutative property of a. So let us consider that delta k be the numerical perturbation generated at kth iterate, and accordingly we can obtain expression 28. So by using the error analysis of first order and after using some algebraic manipulation, we can get an expression 29 and 30, which prove that the sequence generated by 12 is asymptotically stable. Now we will verify theoretical results by using some example, and for that we firstly consider that if we know that if the iteration xk has largest eigenvalue, then the convergence may be slow. So as a result, we can accelerate the convergence of the proposed scheme by scaling. The scaling parameter which is introduced for this purpose as given in equation 31, and accordingly we can obtain a new method named as ALM1, and the stopping criteria used for this example is given in equation 33, and all the numerical examples are performed in Mathematica using this computer specification. uh, so for that we have considered some 10 random matrices which are complex under whose entries are ranging from these two values, and all these matrices are of different sizes and random, and these matrices are considered from some matrix library, that is seed random 50, and the obtained results are given in this table. This table represents the number of iterations required for each method to get converged to sine function. Basically, these first three methods are the compared methods, and the last two methods are the proposed methods. And from this table, we can conclude that the new methods require lesser number of iterations in comparison to the existing methods, and also the CPU time required for the method converts towards sine function is less in the for the new methods in comparison to the existing methods. So we can conclude that the new method is better. So basically a matrix function can be described in variety of methods, but the three most common are polynomial interpolation, the form of Jordan canonical, and the Cauchy integral. But we focus on new iterative approach for such an objective in this study because that is somehow difficult to study. So we basically came up with a new higher order iterative method for finding matrix sign function with no pure imaginary eigenvalues. So, and this method has sixth order of convergence with global convergence behavior as proved by traction scenes. And also the numerical results demonstrate the superiority and applicability of the presented method. These are references. Thanks.